Hi, my name is Carsten Riewerts, and I want to present the paper Dense LIDAR Point Clouds from Room Scale Scans. It is a collaboration with Henry Hansen, Said Mukhalil, Vetle Siderud, and Fredrik Johansen. And we're all from the University of Oslo. So the reason for wanting to do dense room scale reconstruction is that we have as a long-term objective to improve the open source project LS Vision for a couple of use cases. So we would like to improve the image-based reconstruction for tasks like movie post-production, where you can see this little video, for construction review, or for mixed reality. And a particular thing that is not quite as great in LS Vision as it could be is the image-based detection of flat surfaces. So we would like to work in the future on improving its flatness without flattening arbitrary details. So if you wonder who has made that video on the right side, that's by me, Cosimage, the main maintainers of LS Vision and former project partners of ours. So if we work on LS Vision, which we do every day, we need to have a ground truth in order to show that we make progress, in particular in describing surfaces that are not easy for image-based reconstruction. And LIDARs are a desirable data source for this kind of ground truth because they provide a quite high accuracy, and you can get that information in manners that are quite unrelated to image-based reconstruction. So it's an independent ground truth. And when it comes to LIDARs, we have a family of LIDAR scanners that are affordable, that are relying on rotating beams that are scanning the environment. And one example of that is the Velodyne VLP16, which has a resolution of 3,600 pixels horizontally by 16 pixels vertically. And it scans up to a distance of 100 meters. Of course, the resulting image or the resulting data set is a cylinder. So it's not really easy to transform that into a flat surface, which may be desirable if you wanted to have an RGBD representation. There are also front-facing LIDARs, like the Intel RealSense i515, which has a resolution of 1024 by 768 pixels, but it measures only up to a distance of 9 meters accurately. The other thing is, when we started and had the opportunity to buy a LIDAR, it didn't exist yet. So we are living with the VLP16. Now, how does it work? How good is it in actually creating a ground truth for our image-based reconstruction? So this is a set of photographs, just a subset. We had made many more, of a little sofa corner out at Simula. And when we just took these images and fed them into LS Vision's front end, we got a 3D reconstruction out by image-based reconstruction that looks like that. And you may see that even though it's not perfect, there are a lot of details that are not too close to the cameras, that had enough angles. They are pretty well represented. So the sofa, the characters on the sofa and so on, they're all pretty nice. Whereas the reflective surfaces in the front, they are not quite as well done, and the flat ground is actually not so flat in this reconstruction. But how does it look in a LIDAR? Okay, this is the VLP's very own video representation of a sequence of scans. So we moved the LIDAR around while we were recording pixels and fed it straight into the VLP's own recording tool and recorded that as a movie. And as you see, you're basically getting lines. Thing is that if the LIDAR is very close to something like a wall, then you get very dense lines. But for everything else that is further away, you're getting lines with a large distance because the angular distance in the vertical direction just doesn't change. Whereas you can see that the lines themselves are pretty nicely scanned because the horizontal density is very high. But what it also means is that this is definitely not anywhere near the density that we need in order to figure out if the image-based reconstruction has a high quality and if we are satisfied with it. We need to do more. So We know that we have accurate pixel positions, and they may be useful as they are, as with the little resolution that they have in the vertical direction, in an integrated image LIDAR solution. But to understand surface shapes in a ground truth database, the point cloud itself must be densified. And that's what we try to do here. So for local densification, we need to understand first that we absolutely require motion of the LIDAR itself. And that's why we mounted the LIDAR on a tripod. And here we have 3 axes of motion. We have the tilt, the pan, and the roll, where the tilt is a vertical sweep up and down along the y-axis, the z-axis of the LIDAR. The pan is not needed because we have a rotating LIDAR, so we would just rotate around the same axis that it rotates around anyway. And the roll would have been impractical because it would give us a second rotation axis in a different position, making it all the harder to integrate coordinate systems. So we were just using tilting. And then the thing is, we needed to figure out how long is the computing arm. So how long is the arm between the joint of the tripod and the center of the LIDAR, that is our reference coordinate system at any point in time. So basically we use 2 positions of 2 different tilts and measured the distance to the floor at the shortest possible distance. And then we computed the angles, which led us simply to the distance between the LIDAR center and the joint of the tripod. Having that, we could use the IMU, which we mounted on top of the LIDAR, in order to figure out where down was at any given time. Because down is the absolutely most reliable signal that we can get from an IMU. We can use that gravity vector of the IMU at any point in time with a very high confidence. And from just this angle that points downward in relation to the XY plane of the LIDAR, which was identical to the XY plane of the IMU, we could figure out exactly at which angle we were recording every point and where that point was in relation to the parallel plane that is considered our original coordinate system for this position of the LIDAR. And annoying detail, of course, here is that we have to do manual alignment of the IMU cap that sits on top of the LIDAR, because we don't want to break either of these. We want to be able to reuse all of them. Having done that, we have a really nice local densification. We have a really nice local scan that gives us a pretty dense point cloud, but it is insufficient because occlusion is impossible to prevent since the LIDAR is not moving. So we do need a global densification, and that is only possible by moving the entire rig. That means the tripod with the LIDAR and IMU on top. And since we're indoors in closed rooms, neither the GPS is giving us a good information about how we're moving, nor the IMU, which in principle is not very good at doing translational estimates for long distances. So we tried 2 options in order to densify across global motion of the rig. In the first attempt, we used motion path recording that is suitable for continuous recording while the IMU is moving along with the rig, but this motion has to be regular and rather slow. So walking speed is still okay. The second alternative is we just move the LIDAR, we scan again, making another dense scan, and then we discover the new pose directly from a comparison between the 2 point clouds. And that's suitable if we can't do continuous recording or if we have fast and irregular motion. Let's look at point A. We're going to record the motion path. So what we do is we take the entire time of moving from the first to the second position in which we do the dense local scan, and we copy the imagination of frames from images that are leading to a visual SLAM and use them, replace them by segments in time, which we call fragments. And in these fragments, we are collecting a point cloud that only covers a certain range of motion, a certain time during which the IMU and its associated LIDAR is moving in space. We try to compensate for the motion in this little fragment by using the IMU's motion information and correcting for the movement of the individual 3D points. And with that, we have a point cloud for a particular fragment. We find the final pose of the LIDAR in the fragment, using iterative closest point relative to the previous position. If you use generalized ICP as an algorithm, which is rather old, we have one that is super reliable. If you use symmetric ICP, which is from CVPR 2019, we have an approach that is pretty reliable and really fast. In both cases, we get to align the fragments relative to the previous fragment's position, and we can use it in order to generate an entire motion path. This requires fairly slow motion, but walking speed is still okay. Now, having decided what the motion was between the original position and the dense local scan that we did there, towards the second position where we did another dense local scan, we know that we have a motion path that is pretty reliable, and we can use it in order to have a prior, in order to achieve a fairly good overlap between the original and the second dense local scans. And we see an example of that in this little image. We have the green and the blue scans. You see that there is a little offset, which is stemming from the divergence of the motion path from the actual motion. It's a perfect prior for another scan between the two big dense local scans using either generalized or symmetric ICP. And then we have a perfect match because the difference, the similarity between the positions is avoiding that we end up in any local minima that are incorrect and that lead ICP to failure. The second approach uses image height maps. That is inspired by a master thesis that was done in collaboration with the University of Toulouse and Géraldine Morin. And in this approach, we are starting with two local densifications. So we take the first one and we move the LIDAR, and then we take a second dense local scan. Then we extract the planar surfaces from each densification. We train a deep neural network with spherical kernels to recognize flat surfaces. And the training is done with a Stanford 3D large-scale indoor spaces dataset. We discard all surfaces except for candidates for floor, ceiling, and walls. And floor and ceiling can then also be matched very easily because the IMU's gravity vector is super reliable. So the only thing that is questionable in order to figure out how the 2 point clouds should be matched is the rotation and, of course, the absolute translation. So we do now have plane equations for each of the walls, but we want to figure out which wall is which in the two different scans. So what we do is we represent each wall as a 128 by 128 height map. Then we project the 3D points scanned by the LIDAR onto the plane if they're in proximity of this wall. And if there are multiple points, as most of the time is the case, we use the median to resolve conflicts, and then we have a height map. We do bicubic interpolation to a 512 by 512 image, so we upscale this. And then we have such a smooth image that is avoiding the intrinsic errors, measurement error of the LIDAR, that we can easily use Hu moments to match the walls of the 2 point clouds. And these are examples of walls. The upper walls are from one scan, the lower walls from another scan. And I have repeated them because I wanted to write between the different samples the distance of Hu moments, where we just take the Euclidean distance between the 7 parameters of the Hu moment of the particular image. And we see that the distance between images, even if they are quite different visually, but have the same structure, is very, very low. And if we have a different image from a different wall, we are seeing how it's quickly, with how difference here called delta, is rising quite rapidly. So that it means we can easily find the matching walls between the two different point clouds, and we can use those to use the plane equation to get the image, the different point clouds causally aligned. And here we see how that ends up. We have the two different scans, point clouds for the two different scans on the left side. They're causally aligned. We are running another symmetric ICP or generalized ICP. And on the right side, we have the resulting matched point cloud, which again doesn't end up in wrong local minima because we have a very good prior. How good is that densification? Well, on the left side, you see the error of a single scan where the LIDAR has not had any motion at all. It was just pointing at a wall. The 95th percentile of the error was 3.2 centimeters, which is pretty much up to spec of the VLP60. On the right side, you see the error with generalized ICP and symmetric ICP, and you see with 4 centimeters, 95 percentile, and 95 percentile of 3.4 for symmetric, we are very, very close in having a perfect match, as if all of this had been recorded by a single LIDAR. If you look at the final result we get here, it's still coarse so that you can see something and it's not all blue, but we can already see that this is a pretty nice reconstruction of a single room. Unfortunately, Corona hit us when we had only 4 rooms scanned, but we are rather optimistic that this is going to provide us with a rather good ground truth and quite a bit of input for further image-based work. Thank you for your attention.